Hello, my name is Doha. I am a co-author of the presented paper along with Dr. Nassar. Today, I'll present to you our research paper, Segmentation Fault, a Chief Defense Against Adversarial Machine Learning. As you can tell by the title, our research is proposing a new efficient approach to detect adversarial examples. What is an adversarial attack? Applying a certain hardly perceptible pixel perturbation to an image when neural network is driven to misclassify the image. So basically, it is an attack that aims at fooling machine learning classifiers to misclassify an image in question. For example, here we have an image taken from CFAR10 data set. Before adding pixel perturbation, the classifier predicted the correct class of the image. However, after adding the pixel perturbation, the classifier predicted the horse image to be a cat. Okay, now why do adversarial attacks make a threat? Adversarial machine learning imposes a threat in real-world applications concerning people's safety. For example, an adversarial attack that fools traffic sign classification in autonomous cars may cause devastating consequences. However, do we have defense mechanisms? Yes, we do. Several mechanisms have been proposed to this date, such as regularization, data augmentation, ML-LOO. For the purpose of our research, we will focus on the ML-LOO, which stands for multi-layered leave one out. This approach proposes the idea of using feature pixel attribution. This method has shown promising results. However, it suffers a major drawback in time performance. In our paper, we will take a new approach based on optimizing multi-layered leave one out method to improve time performance while maintaining similar adversarial detection accuracies. So for the sake of experimenting, we implemented the multi-layered approach and recorded results, and we will walk step by step through the implementation and findings. But first, let's take a look at the material that we used. We used the CFAR10 dataset, and for the dataset classifier, we used a CNN model that has 26 layers and 94% training accuracy and 89% testing accuracy. And to generate adversarial images, we use the deep fool attack, FGSM, PGD, and CNW attacks from Foolbox on GitHub. Using the Foolbox attacks we mentioned earlier, we generated adversarial images using 30 batches of CFAR10 images. Each batch has 128 images. We did not make a mix of adversarial images, but we generated them separately. For example, we have 30 batches of adversarial images using CNW attacks only, and so on. For each adversarial attack we carried this experiment. We have a data set that consists of equal number of normal and adversarial images from CFAR10. For each image in the data set, we black out one pixel at a time, as shown here. If this was an image and each square is a pixel, we black out one at a time by setting the RGB channels to 0. And each time we black out one pixel, pass the image to CNN model. Now, from here, we branch out to 3 different sub-approaches. So the following steps will be a bit different. So the first sub-approach, we call it the 1D. So what we do here is once we have passed the image to the CNN model, we store the probability of the predicted class, and we keep doing so until we finish going through over all the pixels. Once we're done, we use the stored values to get the interquartile range, IQR. So each image will have a corresponding IQR value. So we use the IQR values as features vector of the corresponding images to train adversarial detection classifier. So our feature vector will look something like this, and it will have a dimension of n1 and corresponds to the number of images, and 1 corresponds to the dimension of the feature vector, and in this case, it is 1. Now, the second sub-approach, we call it the 10D. Here, upon passing the image with the 1 blackout pixel, we store the probabilities of all the classes, which in the case of CFAR10 dataset, we have 10 classes. And also, once we're done going over all the pixels, we use the stored values to get the interquartile range for each class. So each image will have a corresponding vector of IQR values, and there will be 10 IQR values corresponding to each image. And similarly, we use the IQR values as feature vector of their corresponding image to train adversarial detection classifier. So our feature vector will look something like this, and it will have n by 10 dimension. Finally, we have the final sub-approach called the 4KD. In this case, the values of the output layer and a randomly pre-selected set of hidden nodes from different intermediate layers are recorded. We use the stored values to get the interquartile range IQR for each node. So in this case, each image will have 4,000 IQR values, and we will use them as feature vector to train a model to detect adversarial examples. And the feature vector will look something like this with dimension n by 4. Okay, now that we have trained multiple classifiers to detect adversarial images, let's take a look at their accuracies. Well, it seems for us the CMW attack is the easiest to detect, as we have accuracies above 91% with all classifiers using the 1D and the 10D sub-approaches. If we're looking here. We also have, using the XGB classifier here, it did the best in the 4KD sub-approach, and it was remarkably better than what the random forest performed in terms of having accuracy percent, that is 66%. Also, similarly, 10D and the 1D consistently did better than the 4KD approach in terms of recording accuracies along different classifiers. But also, it's worthy of mentioning that the XGB classifiers always did better than the other classifiers. If we look horizontally, these values always better than the values above them that correspond to CVS and random forest accuracy values. And now let's take a look at the time performance of the multi-layered approach. We did not go through the images one by one in our experiment. We went through batches by one batch, and each batch has 128 images. We black out 1 pixel for all the images in the batch and forward propagate the batch at once. So the time taken to compute feature values is in order of 1 minute for 1D and 4KD, and a bit less for the 10D. And just a reminder that we're using very tiny images, 32 by 32 pixels. In real life application, we will have not sure if much, but we will have bigger images of higher resolution. So we can only imagine how long it would take to carry the same process that we carried in this experiment. And also, if we look at the IQR 4KD feature vector, it required 2 GB to be stored. And reminder that we also here using tiny images. So we conclude that the ML-LOO approach isn't very practical in real life application and has major setback in its time performance mainly, and also space requirements. So we took the initiative to introduce an optimization for the multi-layered approach, and we created the segmentation fault method. So essentially, segmentation fault is an approach that aims at improving time performance and memory requirements by using segmentation to segment the images. We black out 1 segment at a time instead of 1 pixel, which leads to reducing the number of blackouts from width times height to n segments, which in turn leads to reducing the processing and memory requirements by a ratio of 10 to 100 in CFAR10 tiny images and more for bigger images. Okay, so we implemented the segmentation fault in our experiment. We followed the same steps as in our multi-layered implementation. However, we segmented our images using 3 different segmentation methods and created 3 data sets in each of blacking out, instead of blacking out each pixel of the 1024 pixels to compute the AQR features vector of each image, we black out each segment out of the total number of segments that did not exceed 300 segments per image. We can already see that we reduced the loops from 1024 times to 300 times maximum. But first, let's take a look at the segmentation methods that we used. First, you have the filled in swab. It has 1 parameter scale. The higher the scale means less and larger segmentation, as shown evidently by the experiments we carried and recorded in this table. The second segmentation method was quick shift. It has 2 parameters, sigma and max dist. As the value of these parameters increase, the number of segments decreases. If you look at the table in the example of the bird image, when sigma was set to 0 and max dist was set to 10, the lowest values in our experiment, we had 224 segments, but when we increase the sigma to 2 and the max dist to 20, the number of segments decreased to 11 segments. Finally, we have the slick segmentation method. It has 1 main parameter, that is the end segment, which controls the number of segments in an image. Okay, for conducting our experiment on each segmentation method, for each experiment that corresponds to a different attack, we used 3 batches of benign images and 3 batches of adversarial samples, which add up to roughly 8,000 images, which is exactly what we did for our multi-layered approach, multi-layered implementation. We use multiple epsilons for attacks, increasingly from 0.02 to 0.04 to 0.1. And we use 80% of the data set to train our model and 20% for testing. Okay. Since earlier we noticed that the XGB classifier always performed better than the other classifiers, we only use the XGB classifier in this part of our experiment. And we recorded the AUC values for different AQR representation and different segmentation techniques. Now, the first thing that we notice in this table is that the results related to the 4KD sub-approach almost always recorded the highest accuracies along the 3 segmentation methods, followed by the 10D and then the 1D sub-approach. And notice that we set darker shade of gray for higher values, so you can see the gradient of gray from darker to lighter when we're moving from 4KD sub-approach to 1D sub-approach. Okay. Also, we observed that changing the parameters, those parameters, value of our segmentation method did not really result in drastic difference in the accuracies of values, as we can see. Okay, also, it is worth mentioning that accuracies recorded when the scale parameter in the fills and swab segmentation was set to 1000, the accuracy was lowest compared to those corresponding to scale values that were lower than 1000. Now, the quick shift segmentation method did not show a consistent pattern of change in the classifier's accuracies with respect to increasing and decreasing these 2 parameters, sigma and max dist. However, as for the slick segmentation method, generally we noticed that as we increase the end segment value, the accuracies of our classifiers increase. Now, our priority concern here is if the accuracies of our classifiers that we trained after using the segmentation fault approach are similar to the accuracies resulting from following the multi-layered method. And we observed that generally, the accuracies corresponding to different segmentation methods using different parameter values are more or less very similar to the relevant accuracies achieved by using the multi-layered approach. For example, if we look at the multi-layered approach with the FGSM, we have an 87.1%. If we look at the SLIC in our segmentation fault approach, in the 4KD sub-approach, we have the highest, with n segments set to 32, the highest accuracy is 86%, very similar to 87, and the lowest 85. And also another example, if we look at the 4KD, the 10D, let's go for the 10D in the CW, the multi-layered approach recorded 96.7%, while in the SLIC we recorded, when the n segments was 128, we recorded 95.9%, which around 96%. This is the highest, and the lowest was 93.4%. So we can see we have very, very similar accuracies. Okay, here we are considering the time and the memory performance to extract IQR feature of the, sorry. Here we are considering the time and the memory performance to extract IQR feature vector of one CFAR10 batch that contains 128 images. Now let's take a look at the time performance we achieved with segmentation fault by comparing the multi-layered time performance with those corresponding to individual segmentation methods. Starting with the Filden's swirl, we can observe an incredible improvement in the time throughout all the representations, 1D, 10D, and 4D, compared to the ML-LOO here. While the multi-layered approach recorded 1 minute and 20 seconds in the 1D representation using Filden's swirl, the highest time recorded was 2.24 seconds, and the lowest was 1.9. And in the 10D approach, in the 10D sub-approach or representation, the multi-layered method recorded 45 seconds to compute the IQR feature vector, while in the Filden's swirl, the lowest time recorded was 0.7, while the highest time was 1.63, which again, very incredible improvement. Now, as for the SLIC segmentation, also very similarly, it's not as good as Filden's swirl, but still very remarkable improvement, as we have in the 10D representation, highest value 5.9 and the lowest 1.42. While in the multi-layered approach, it was 45 seconds. In the quick shift approach, although there was an improvement, but it was not as astonishing as we found it in the SLIC and the Filden's swirl segmentation method. And similarly, in the memory requirements improvement, it was also reduced a lot when using the segmentation fault over using the multi-layered approach. In some cases, for example, in the multi-layered approach in the 4KD, we required 2 gigabytes to store the feature vector. But when using the segmentation fault, we dropped down to a whole smaller unit. And this is a great improvement, and similarly can be observed with a different representation using different segmentation methods. So what we can conclude from this experiment, the segmentation fault requires much less memory. And using a GB classifier 4KD feature vector representation recorded the highest adversarial classification accuracies. Also, the 10D is consistently the fastest to execute since it does not require post-processing beyond forward propagation through the classifiers. This is also something we observed here, that the 10D was always recording less time than 1D and 4KD. The 10D requires 10 times more memory than 1D, and the 4KD requires 381 times more memory than 10D. In conclusion, the multi-layered approach is a simple defense to wipe out most adversarial samples that was extensively tested against different attack techniques and mixtures of parameters. Nevertheless, the computational cost and memory requirements cannot be disregarded. In this paper, we proposed a resource optimization approach based on segmentation. Our approach permits a considerable improvement in source efficiency while maintaining the originally main property of multi-layered approach, a simple and efficient adversarial detection that quickly wipes out most adversarial samples. Thank you for your time and thank you for listening, and we hope that you are pleased with our research.